you have to regroup them into 4 bits. Why? Because we are converting the octal to hexadecimal. That's why it should be combination or collection of 4 bits. See what is this computer codes is all about. Mainly this computer codes will going to help us in order to represent the character in a coded form in the memory of the computer. Well, if I am pressing any of a key in a keyboard, then that will be converted into its equivalent ASCII code. Again, it will be converted into binary. That's what computer understand. Hello everybody, a warm welcome to one and all. Welcome back to the session 8 on the unit 1 of BCA's first semester. Subject called Fundamentals of Computers. I'm Rohini TS, Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence, MYSURU. So in our today's session, let me continue with the number system itself. Before that, we'll just have a quick recap of our previous session. As we know that in the last session of this unit, we had a discussion regarding these many topics. We got to know how we are going to convert from decimal to hexa, hexa to decimal, binary to octal, and octal to binary, then binary to hexadecimal, and then hexadecimal to binary. So all these we got to know in our last session. So in our today's session, we're going to see the conversion from octal number to hexadecimal number system. That is what conversion from any other number system than decimal to any other number system than decimal. So we are converting from octal to hexa and then hexadecimal to octal, and also we'll see about the computer codes. What do you mean by computer codes? How it will going to helpful, and what are the different types of computer codes we have. Let me get into the session. That's all regarding conversion from octal number to hexadecimal number. Octal in the sense what? That will totally comprises of 8 digits, that is from 0 to 7, and hexadecimal in the sense it is of 15 characters, 0 to 15, out of that 0 to 9 and then A to F. So whenever I am converting from octal to hexadecimal, at the time you can expect the resultant which will be in between 0 to 9 and A to F. Then how we have to convert? We'll see the example along with the steps here. So by making use of a binary system, that is what comprises of 0 and 1, we can easily convert this hexadecimal to octal and octal to hexadecimal. What is the first step then? Write the binary equivalent of each octal digit. Already you know how to convert octal to binary, right? If I am giving 4, then what is equivalent of binary? You have to take 4 to 1 format. So if it is 4, 1, 0, 0. In the same way, we have to write the binary equivalent of each octal number here. After that, you have to regroup them into 4 bits. Why? Because we are converting the octal to hexadecimal. That's why it should be combination or collection of 4 bits. Hexa in the sense 15 digit, 8, 4, 2, 1, 8 plus 4, 12, 12 plus 2, 14, 14 plus 1, 15. So that we have to make a regroup of 4 bits here from the right side with zeros added if necessary. From the right side, we have to do this grouping. If zeros are necessary, if we are unable to make a group of 4, then we have to add 4 zeros to the left side if it is necessary. Then in the step 3, convert each group into its equivalent hexadecimal digit. So already you know about the number system table. If it is 0, 0, 0, 1, then that is equal to 1. If it is 1, 1, 1, 1, that is equal to 15. In the hexadecimal, 15 means F. So in that way we are going to do the conversion. We'll see the example, then you will be able to understand. So here my question is what? 274, which is of base 8. Now it should be converted into its equivalent hexadecimal number. Fine. What is the first step? I have to write the equivalent of this octal digit. What is 4 to 1 format? You go with 4 to 1 format. In order to get 2, we have to add this 2 only. That's why this becomes 0, 1, 0. Next what we have? 7, that represents 444. 4 plus 2, 6. 6 plus 1, 7. Then we have 4. 4 is what? By adding 4 only I can get. Remaining 2 values will be 0 and 0. So now what I got? 0, 1, 0, 111, 1, 00. Let me write it together now. Here it is of 0, 1, 0, second number 311, then this is 100. So after writing all the binary equivalent of this octal digit, we have to reframe or regroup of 4 digits. Let me consider this 4 digit as 1 digit, then these 4, fine. I'm left out with only 1 0. So I have to write 3 consecutive zeros for it. Okay. So now I have to write the equivalent of this hexadecimal number. 4 zeros in the sense what? 0 itself, and then this is 1011. 8421. 8 plus 2, 10, 10 plus 1, 11. So if it is 11 in the hexadecimal, 11 in the sense which one? The letter B. That's why I will write it as B, and now it become 8421, it will become 12. So if B is 11, then C should be 12 itself. So I am going to write C. So this 0 is negligible here. That's why the equivalent is what? BC, which is of base 16. Okay. Therefore, what is the equivalent then? Therefore, 274 of base 8 is equal to BC of base 16. Okay. This is how we are going to convert from octal to hexadecimal number. So, that is what the steps I had written here. This is how we are going to convert from octal to hexadecimal. Next, we'll see the vice versa of it. That is what? From hexadecimal to octal. It is just a reverse of that. Here also we are going to use a binary number system in order to convert this. What is this step 1 then? Write the binary equivalent of each hexadecimal digit. So here input is what? Hexadecimal. After the conversion, we are going to get octal number. So that we have to write the binary equivalent of each hexadecimal number. After that, we have to make it as a group of 3. Why? Because in the octal number system, up to 7 we can have, that is 4 to 1 format. We have to make a regroup of 3 bits from the right side, and we have to add 0 if it is necessary, or if we are unable to make a group of 3 binary digits, then we should add that 0, and we have to convert each group into its equivalent octal digit. We'll see the first question. So here we have a question that is FADE, fade, which is of base 16. Now we have to convert that into octal number. Fine. What do you mean by F here? That is equivalent to 15 in the hexadecimal. So if it is equivalent to 15, by making use of 8421 format, then it will be what? 1111 A, that is 10. 8 plus 2 will be 10, 1010 for D, 1101 for E, that is 14, 1110. Fine. After this, we are going to get the answer like this. This is what? Binary conversion. Now we have to use, or we have to make a regroup of 3 digits from this what? Consecutive zeros and ones, which is equivalent to binary. So here we had written all these things. Now I am going to make a group of 3 digits from the rightmost bit. So this will become one group, and these 3 become another group, these 3 become one more group, these 3 and these 3. I am left out with only 1 digit now, so I should add 000 for it. That is what I had written here. 001 and 111, 101, then 011, 110. So if you are using 4 to 1 format, what is the equivalent of this 001? That is 1, 111 is nothing but 7, and 101 is nothing but 5. Then 011 is 2 plus 1, 3, and 110 is 4 plus 2, 6. So it become what? 17536, which is of base 8. Okay. Whatever we have a hexadecimal, write its equivalent 4-digit value, make it as a collection of zeros and ones as a binary, and make a regroup of the 3-bit digits here. Then you will be able to get the equivalent octal number. Okay. So you try with this face, and try with one more number, AB.1C. Try to convert this into octal. Okay. Let me move to the next type. That's all regarding what? Computer codes. So till now we got to know how we are going to convert from decimal to any other number system to decimal, and any other number system than decimal to any other number system than decimal. So till now we have learned all kind of conversion. So after that we have a new concept, that's all regarding computer codes. Then why we require this computer codes? What computer can understand easily? That's what binary number, zeros and ones. So we have a different schemes, or we have a different methodology in order to represent the characters, number, digits, even special symbols. By making use of certain schemes or what type of methodology, we can represent it. So now let's see what is this computer codes is all about. Mainly this computer codes will going to help us in order to represent the character in a coded form in the memory of the computer. So we are using this computer code. We have certain methodology or a scheme. By making use of it, we are representing a character or any of the digit, symbols, whatever it could be. Any character we are represented in the terms of coded form, which easily can be understood by the computer. That's why it will going to be stored in the computer memory, and we have certain coding schemas here. In it include BCD or binary coded decimal. Second one EBCDIC, that is what extended binary coded decimal interchange code. And here we have a ASCII, that is American Standard Code for Information Interchange. Then we have a XS3, and also we have a UNICODE. We also have this UNICODE. Along with that, we have different kinds of scheme of coding or computer codes. By making use of that, we are going to represent the characters in the coded form of a computer memory. We'll see the first one. That's all regarding binary coded decimal number. In short, it is BCD. Already you know about 8421 format, right? That is what the same thing which we are using in the BCD format. So it's a system in which decimal numbers from 0 to 9 are represented by a 4-bit binary number. So that's why we are calling it as a BCD number system. So we are using 4-bit binary equivalent number in order to represent any value which is between 0 to 9. So here each bit of BCD has a positional weight. Why? Because 2 power 0, 2 power 1, 2 power 2, that is what? If it is 2 power 0, 2 power 0, then it is equal to 1. If it is 2 power 1, then 2, then 2 power 2, then it will be 4. 2 power 3, then it become 8. That is what 8421 format. We are going to keep on increasing by 1. So the weights are assigned as per the position which is occupied by the digit. It will start with a 2 power 0, 2 power 1 up to 2 power n minus 1, so that we are going to use a format called 8421. That's why this BCD number system is also called as what? 8421 code. So here you can see the representation of a decimal number from 0 to 15 in a binary and its equivalent binary coded decimal. That is what you can see here. Binary system and binary coded decimal system both are not same. So we are going to use 4-bit binary number in order to represent each number. For example, if it is 15, so in the terms of what binary number, then it will become a 1111. Isn't it? But in the terms of BCD, this 4 is represented with a 4 codes, and this 5 is again separately represented with another 4 digit. So for this it will be 0001. How we are going to represent 5? That will be 0101. So in this manner we are going to represent. So here you can see the example or what conversion from binary decimal, binary and BCD or a binary coded equivalent here. So you can see here up to this 9 no changes, and after the 9 we have a 10. 1 is what 0001 and 0 is 0000. So we are going to represent each digit separately in the BCD or binary coded decimal. Fine. We'll go to the next type. That's all regarding gray code. This is what comes under non-weighted code, and it is cyclic as well. Non-weighted in the sense what? It is not going to have any position in order to specify its weightage. Mainly it is referred as a cyclic because successive code words in this code differ by only 1 bit position. So that is what we are considering this as a unit distance code. Okay, so if the previous code is 000 and next code will be 0001, so there will be only one position, or there will be only one word changes in this particular type of code, and we are also calling it as a reflective in nature. And where we are going to use this gray code, it is used in many practical application like analog to digital conversion and units distance measurement. So in all those kind of things, we are going to have this gray code. Then what is the next type? That's all regarding ASCII, or American Standard Code for Information Interchange. So we are going to use this kind of computer code in order to represent the text. That text can be any number from capital A to Z, small a to Z, 0 to 9, or combination of any number, and it is also able to represent the symbols. Along with that, it will going to have any of the combination of numbers or digits, alphabets, uppercase, lowercase, or any special symbols. Everything can be represented with the help of this ASCII. This is what a standard. For example, if I am pressing any of a key in a keyboard, then that will be converted into its equivalent ASCII code. Again, it will be converted into binary. That's what computer understand. So here you can see that when there is a piece of text, this ASCII will going to convert each character to a number. So it is using numbers in order to represent each character which we are giving as a text here. So that's why the set of numbers is easy to store into the computer's memory. Instead of storing alphabets or symbols, if it is having certain equivalent number value, then it will be easy to store in a computer. That's why assigning a number to a character is called as what? Encoding. So we are having more confidentiality to the data. We are making it encoding. And if you take the example, capital letter A. So if you have a capital letter A that is assigned to a number 65, then what is C? Then it will be 67. For D, it will be 68. For whatever the character you have, either 0 to 9 or a combination of any numbers. So if it is capital A to Z, small a to Z, for every numbers, every symbols, every digits, you have equivalent ASCII value. This is what one of the example. Okay, and mainly this ASCII code will going to represent by making use of 7 bits. Then it becomes 2 power 7. So if it is 2 power 7, then it is able to represent maximum of 128 characters. Okay, that's all regarding what? ASCII codes. Next we have a last one. That's all regarding Unicode. This is what slightly different from the ASCII code, but it will going to have more weightage. Why? Because it is able to represent maximum number of character. If ASCII code is represented only the numbers 0 to 9 or alphabets, capital A to small letter A to Z. If that is the thing, this Unicode is slightly different than the ASCII code, but it will going to have more weightage here. It's just an alternative. It is maintained by Unicode Consortium. So this is maintained by Unicode Consortium, and it will mainly going to cover a range of character, that is wide range of character it is going to cover, and then it contains the representation for letters in the languages. So here one more add-on weightage to the Unicode. It is able to represent the characters in the language English, Greek, Arabic, etc. And also it is able to represent the mathematical symbols, even emojis, and then many more. That's why this Unicode has more weightage than the ASCII code. And also we have different types of encoding here. That is what we are giving number in order to represent any character. That is what encoding. So we have 3 types of encoding in this Unicode: UTF-8 and UTF-16 and UTF-32. So this what 8, 16 and 32 represent, that will going to use us 8 bits per second, 16 bit per second and 32 bits per second. In order to represent the character, we are using these many bits of memory in the computer. That is what this all regarding Unicode. So here you can see some more information regarding the Unicode here. And also if it is UTF-F, the first 128 characters are only ASCII character. Why? Because if it is 2 power 7, then it is able to represent up to 128. So then that's why this ASCII is also comes under UTF-8 Unicode method or encoding method. So here This Unicode is also going to be used in internationalization and localization of computer software. Why? Because it will going to assign certain standard value for all the kinds of character, and also we are going to use this Unicode standards in operating system, XML, .NET framework, and also in some of the programming languages like Java. Okay, so there and all we can have this Unicode computer codes methodology or scheme. I hope you all understood regarding computer codes. So here you can see the difference between ASCII code and Unicode. So that's all regarding what computer codes. Let me meet you in the next session with the content of this Boolean algebra. Until that, keep learning, keep on growing. Thank you.